Okay, I'm back and I want to jump to this maximum power transfer. I'm skipping over several similar problems that you guys ought to know how to do. So be sure and go back over them in your handouts and try them on your own. But now we want to look at how much power can we get through a circuit. We look at the Thevenin's equivalent. Open circuit voltage, closed circuit current, or excuse me, impedance, output impedance, and load impedance. Voltage across the load, voltage across the impedance. And we want to maximize the power. Power expression will be given by power in the load, 1/2 amplitude voltage, current times the cosine of the difference in the phase angle between the two. Okay, and this expresses it in terms of absolute values. The impedance of the load is given by the real part, which is the resistive part, RL. This is something new. I don't think we've seen before. It's called reactance. It's the imaginary part of the impedance. That's all it is, imaginary part of the impedance. So let's go through here. Voltage across the load is just given by the voltage divider equation. Current across the load is given by the voltage across the load divided by ZL. So we express it in terms of magnitudes. Magnitude of VL is the magnitude of the voltage divider impedances times VOC. Angle of IL is the difference between the angles of the two, which is what both these equations are expressing. And the magnitude of IL is just the magnitude of VL over ZL. Okay. A trig identity. The cosine of the angle is going to be 1 divided by the square root of 1 plus tangent squared of the angle. So we can get the tangent of the angle given by this, and we can get the cosine of the difference is going to equal, you'll notice that's where this comes in. The difference in angles is going to be delta ZL is going to be the difference between the voltage and the current angles. That's what this is trying to say. So we're working with the angle of the impedance, which is going to tell us the difference in the voltage and current phase angles. And using this trig identity right here, we can go from here to here. Just plug in the formulas into here. PL, VL, which is given, here's VL, which is, partially this expression. IL times IL, you have a 1 over ZL here. So let's go ahead and write this. Magnitude of ZL So that's IL. This is the VL part. This is the ZL part. VL, ZL. So now when we multiply this times this, we're just going to get one term in ZL, VOC squared, ZL plus ZTH squared. So we get the magnitude of IL times the magnitude of VL here, the 1/2 out front, and the cosine of the difference between the angles given by this guy right here. And we got the equation. I'm going to do some erasing. Now we're back, and the next step. So we notice that we have a cancellation, and we can write this ZL plus ZTH squared in terms of resistances and reactances. Okay, so PL, the power consumed by the load, we put everything together. ZL plus ZTH squared right here. VOC squared, RL on the top and the 1/2 factor out front. Now I better do some erasing. There we go. And we differentiate dPL dXL and dPL dRL equals 0. We want our power to be maximized. We only have two independent variables, or two independent variables here. VOC is a given. RL is independent. RTH would also be a given. It depends on the source. So we only have two independent variables, RL and XL. Do the differentiation, set them both to 0. And when you crunch the numbers, this is what you get. That the optimum for maximum power coupling, for maximum power to get out of here and into here, maximum power coupling, we want the load impedance to be the complex conjugate of the source impedance. And then when you do the substitution, when you substitute these values here back into PL right here, you get this formula. Okay. Now, find an example. Here's an example. Find what the load has to be for maximum average power transfer and compute it. So the first thing we do is figure out what is Thevenin's equivalent impedance for this network right there. So we have a inductor, a resistor, and a second resistor. And we need to know this impedance. This is J, ohms, 2 ohms, and 4 ohms. So it's just these two in parallel. 2 plus J times 4, all divided by 6. 2 plus 4 plus J. And we go through a bunch of math, and I'll pick it up next time. This is a good place just to stop, set up the problem, and then we'll pick up the problem next time.